knocking. And there have been multiple technologies implemented or designed by automotive engineers, industries to improve the efficiency and reduce emissions. Nowadays, predominantly it's engine downsizing, essentially to reduce the size of the engine, combined with boosting as an efficient low-cost solution. These are all some of the technologies that are being tried at various levels by industry, and they are given as a projection of the likelihood of these technologies being implemented in the future. This is a basic primer of how the SI engine combustion looks like. This is your internal combustion engine scores. In an SI engine, air and fuel mixture is drawn inside the engine cylinder and it combusts. However, in case of an abnormal combustion or an engine knocking condition, what happens is inside this engine cylinder, there will be, because of high temperature, before the spark ignites and completely combust the remaining portion of the unburned fuel, there are some pockets which are at high temperature and which ignite simultaneously, thereby creating huge pressure fluctuation. And this is called knocking, engine knock. This is actually a function of temperature, and higher the temperature of the burned charge, higher the temperature of the unburned charge, then more is the propensity to knock. So what happens because of this is higher temperatures will lead to higher knocking tendency, and the effect of that would be on the it will result in damage of the engine and also efficiency loss and all. So the prime factor is here the temperature. So what strategies are implemented is for knock mitigation is spark is generally timed slightly later. Spark is given ignited at a slightly later time, or the conditions ensuring that the temperature remains at a slightly lower level. Any strategy that can slightly reduce the temperature will be useful to reduce the knocking tendency. So there are various techniques that have been used to mitigate engine knock. So some of the current technologies are, as I was initially talking about, downsized engines, fuel enrichment or premium fuels. So there are some fuels which are high premium fuels which are being used as well, but they are slightly expensive. And another strategy is exhaust gas recirculation. So part of the gas that goes out of the exhaust of an engine is recirculated back into the engine cylinder or through the intake port. So that kind of reduces the knocking tendency. Spark timing retard. So as I was talking to in the previous slide, you can retard the spark timing and essentially reduce the knocking tendency because it will ignite at a slightly later stage where the temperatures are not so high. Advanced technologies are water injection, water alcohol blends, are changing the different cycle, Atkinson cycle. So my focus of research during my PhD was on this technique, water injection and water alcohol blends. So what we do here is we use the principle, or we use the property of water to cool down the temperature inside the engine cylinder. So this is an example of how a water injection looks like. So what essentially this is, what essentially is taking place inside this engine cylinder is water is being injected as a fine spray. When it is injected as a fine spray into the air, incoming air, what happens is it vaporizes, taking heat from the air or exchanging energy from the air. And then what happens, the air that goes inside the engine cylinder goes at a slightly lower temperature. And if it goes at a lower temperature, then when it comes up during compression, it will still be at a slightly lower temperature than if it had not exchanged energy with water. So we are using water injection to reduce the temperature inside the engine cylinder. And if we are able to mitigate knock, then we can play around with the spark timing. We can play around with all the other controls to try to improve the efficiency. So the property wise, how does it look like is normally gasoline or the petrol that we use in the engines, it has a latent heat of vaporization of close to 350 to 400 kilojoules per kg. Whereas other fuels, biofuels like ethanol, methanol, they also have slightly higher latent heat of vaporization, whereas water has the highest latent heat of vaporization. So 20 to 60 kilojoules per kilogram. So it is much higher than gasoline. So if it vaporizes, the temperature inside the engine cylinder drops down considerably. So my point of interest was using water and water methanol blends. Methanol is again an alternate fuel, and then what we can see with respect to the efficiency or the emissions perspective. So with that, this is an overview of my research. Essentially, this is a slightly busy slide, so let me walk you through this slowly. First step was I developed an analytical model to understand the impact of water injection on cycle efficiency. So this is based on the principles of conservation of energy. What is the energy associated with water and how it vaporizes, and when it vaporizes, what happens to the energy transfer, so on and so forth. And then the next one is high-speed imaging to characterize water sprays. Once we understand how much water is needed, or what effect does it have on the cycle, how do we look at the imaging, high-speed imaging? And then the water injection was tried on an engine, on a single-cylinder engine, research engine, and then tried to understand how does it impact the performance. So first, I'll talk about the analytical model. So this is the analytical model. Essentially, it is an ideal cycle analysis to understand the impact of water injection on the efficiency of a constant volume cycle. So this is a constant volume cycle that you might be aware of. So the red cycle, a thermodynamic cycle, is a constant volume cycle which does not have any water injection in it. So it has a process of 1 to 3 is isentropic compression, then constant volume heat addition, 4 to 5 is isentropic expansion, followed by constant volume heat rejection. So this is an ideal condition that we're trying to understand. Now, what I'm doing is I'm trying to inject water at different locations during the compression stroke. Piston is moving up in the compression stroke, and I'm trying to inject water at different conditions. Now, what happens because of that is, because water is injected at certain location, what happens, it cools down the air and fuel mixture. It cools down, so the temperature drops and the pressure drops simultaneously. And what happens because of that is it starts to get compressed along this line. So the red line cycle is the cycle without water injection, whereas the cycle with black lines is the cycle with water injection. So 1 to 2 is the point where compression takes place of the air fuel mixture, and then water is injected, then it compresses to 3 prime, then it goes to 4 prime and 5 prime. So what we're doing here is essentially we are trying to reduce the compression work. Once we reduce the compression work, then we will be able to improve the efficiency, is what we try to see. So this is how it looks like on an engine cylinder, different locations where water is injected. So the principle for the conservation of energy, how we approach this is based on the state conditions of water. So this is how the thermodynamic states of water with direct injection of water inside the engine cylinder looks like. Water is injected at a pressure of close to 3 to 4 bar. A fine spray of water is injected into the engine cylinder. And what happens is state 2, this is when the water was injected. Air and fuel mixture is inside the engine cylinder and water is inside the injector. And then this is an intermediate state where air and fuel mixture is inside the cylinder and water is also existing as a liquid inside the engine cylinder. It's just injected, but it is a temporary state or a transient state where it exists as a liquid. Then the moment it is injected into the cylinder, the assumption is that the water vaporizes completely, instantaneously, and reaches 0.2 prime. So essentially what happens is the transition is taking place from 2 to 2 prime, and it is independent of the path followed, because this is just essentially an energy transfer. Energy transfer between air fuel mixture and water is taking place. Nothing else is being is carried out. So these are some of the metrics that we try to understand. First one is drop in temperature due to charge cooling, and then saturation pressure ratio. So how much amount of water is being injected into it, to what is the saturation pressure of the water at that condition. It essentially tells you what the how far is the water away from its saturation limit. Then thermodynamic cycle efficiency, which is the total cycle net work divided by heat supplied. And then water fuel ratio is the amount of water, mass of water to the mass flow rate of fuel. So what you're seeing here on this plot is water is injected at different locations. 30 degrees before the top dead center. Top dead center is when the piston reaches the top. 45 degrees before top dead center, 60, 90, and 120. Now you can visualize the temperatures of the engine when the water is injected at 120. It is just it. What it literally means is the piston is slowly going up towards the top dead center, and it is still traversing a lot. So at 120, the temperatures will be much lower. The temperatures inside the engine cylinder will be much lower than it is at 30. So what it essentially are, consequently, what happens because of that is at 120, because the temperature inside the cylinder is so low, you cannot vaporize more amount of water by injecting it into the cylinder. That is what you see here. What you see here is the partial pressure of water to the saturation pressure of water vapor at that condition. So if you inject only 0.35 or zero point 0.4 amount of water, then what happens is you will reach the saturation point. Any more addition of water will make sure that there is no evaporation taking place. So as you go along, if you inject it slightly later, because the engine temperatures are slightly higher, you will be able to evaporate water more in more quantity. So essentially, this plot shows the limiting quantity. It is just that at 30 degrees before the top dead center, you can inject 1.73 times the amount of fuel. So you, as you inject it later during the compression stroke, you can inject more. But in reality, there is a problem. The problem is that if you are injecting very close to the top dead center, then you will not have enough time for the water to vaporize. So because water vaporization is not going to take place instantaneously, it needs temperature as well as time. There is a trade-off between injecting too early. We will be losing out on temperature. We will not be able to evaporate more quantity. But if we inject it late, we'll not be able to evaporate faster because we do not have enough time. So there is a trade-off there. And that trade-off is reflected in the cycle efficiency. When we see the cycle efficiency, this is exactly what happens to the cycle efficiency. If you inject too early, then what happens is, although you are injecting it at a slightly lower temperature, you are not able to inject too much amount of water. However, there is a significant difference, or there is a significant reduction in the compression work, due to which the ideal cycle efficiency increases at 120 degrees before top dead center. And if you start to inject it slightly later from 120 to 90, 90 to 60, you can see that the efficiency starts to drop down to without the water injection condition. And if you inject at 45 or at 30, then you'll not be able to get any benefit out of injecting more amount of water. Although you can inject more amount, because the in-cylinder temperatures are higher, you'll still not be able to get any benefit out of it. So that was the ideal analysis. Then we wanted to see how does it look like in a spray. How do we characterize the spray? Does it exactly behave the same way as what we are seeing in an ideal case? It's essentially a yardstick. So I'll briefly touch upon the high-speed imaging to characterize water sprays. We wanted to explain or understand the spray characteristics of the water sprays. This is a constant volume spray and combustion vessel that we had at Michigan Tech. This is essentially a spray vessel which is used to look at the sprays by using a high-speed camera. So this is a spray vessel to visualize sprays at engine conditions. This has 6 sapphire windows, one here, one on this side, one on this side, one on the other side, and one down and one on the top. So these sapphire windows are for optical visualization. Light is incident on this, and then a collimated light passes through the injection. And what happens is, because there is some physical phenomena in terms of vaporization that leads to change in refractive indices, and because of density gradients, it will lead to understanding something about how vaporization is taking place. So we captured the spray images using a high-speed camera, and we used pure water. Water was just injected from an injector, and then we used 50% water and 50% methanol by volume. Methanol was also mixed with water. Why do we mix water with methanol? Is because methanol actually vaporizes at a slightly, or it has a lower boiling point than water, right? So it vaporizes at a lower temperature. So we wanted to see if water doesn't vaporize, can we improve vaporization by adding methanol? So the high speed images were captured at 16,000 frames per second. So these are high speed, expensive cameras which can be used to capture these sprays. This is the optical diagnostic system that was used. Two concave mirrors are essentially used to send collimated light through the spray combustion vessel. What I'm showing here is this one, this spray vessel. Here the injector is on the other side of this spray vessel. So there is a similar window on the other side, and injection takes place inside and it comes onto this. So a light source was kept here, a light source was kept on the other side, which passes through the concave mirror, goes through as a collimated beam, and then it is captured through a high-speed camera. So the injector that we used to inject water was a Bosch production injector. This is the normal injector that is used in almost all the gasoline engine cars and all. So what we are trying to replicate is trying to replicate the conditions that exist inside the engine. So at 60 degrees before top dead center, you will have some conditions of the air and fuel mixture, some temperature and pressure, which is what you see here. So this is the temperature and pressure when the piston is close to bottom dead center, when it is going up at 90 degrees before top dead center, at 60 degrees before top dead center. So what we're trying to do is maintaining the conditions of this pressure and temperature for each case inside that spray vessel, and injecting water into that spray vessel where the pressure and temperature are so and so. Injection was done at 200 bar. So water was injected at 200 bar. The injected temperature was 90 degrees. We use Mie scattering and Schlieren techniques to capture these images. So this is this. I'll show you this point. So 60 degrees, what would be the pressure and temperature, and how does the spray look like at this condition? This is a Mie scattering and Schlieren imaging. What it does is it shows the amount of liquid and vapor region. The Schlieren imaging shows the liquid and vapor region, whereas the Mie scattering shows the liquid region. So what you are seeing here is a certain amount of water being injected into this constant volume spray vessel. It is the same spray vessel that I just showed in a couple of slides before. So I'm injecting water into this vessel, and the conditions inside the vessel are that the pressure is 9.1 bar, the temperature is 170 degrees C, and I'm injecting water into that, and I'm trying to understand if there is some enough vaporization taking place. Now, if you can see, you see now the water is coming out in large quantities here. It is still coming out as large droplets, and you can see very clearly here as well as on this side, it is hitting the walls of the spray vessel. So which means that even though it is coming out, it's not evaporating before it hits the wall. So there is enough amount of liquid that is hitting the wall. So this is one important observation that we saw, even at slightly lower amount of water that was sent in. Then we added, as I initially talked about, we added methanol and tried to replicate the same conditions, try to inject water, try to inject water and methanol mixture, and try to see if we are able to improve the vaporization, whether it still vaporizes faster or it still goes and hits the walls of the combustion vessel. So from the images, we can see, or from the video, we can very clearly see that it is still taking time to vaporize, and it's still not vaporizing completely. So what it essentially means is, even after injecting, like now you can see here 8.5 milliseconds after injection, now it's still going further, 10 milliseconds, 12 milliseconds. Now you just have to understand that cycle time, one thermodynamic cycle inside an engine takes close to 30 to 40 milliseconds. So if it is still taking this much time to completely vaporize, then it means that it will not be able to vaporize completely. So the outcome of this study, or this spray imaging, is that visually we are not able to see some vaporization taking place completely. And now what I do is I superimpose an engine. This is how an engine configuration looks like. A schematic of an engine configuration looks like. The piston is at 60 degrees before top dead center. If I have this engine configuration, now you see when the spray is injected, how it is hitting the pistons of the cylinder. So this is an illustration that with this water injection coming from a 6-hole injector, at these conditions, we will not be able to vaporize all the water completely. And there will be a lot of amount of water that is being hitting on the piston. And that is actually not a good thing. Water hitting the piston as a liquid, it will result in corrosion, and as well as many other problems with respect to emissions. There are many other multitudes of problems. So this kind of shows and illustrates very clearly that this is not a very optimum condition for complete vaporization of water. Now, quantitatively, what I do here is I analyze these high-speed images in MATLAB, and I try to understand or quantify the spray character. Now, once we understood the ideal cycle impacts, and then we characterize the spray, we try to understand at what conditions will it be useful. Then what we did was put this on an engine. So we have a single cylinder engine at Michigan Tech, and what we did essentially was we have fuel that goes through the engine cylinder where it is injected, and then we have another injector for water injection, and then we inject this water inside at different quantities, and then see how does the engine performance look like. So this is an overview of the engine studies with water and water methanol blends. So this is a single cylinder research engine, SCRE. It has a displacement of 0.55 liters or 550 cc at a compression ratio of 10.9:1. It has two injectors, facilities for two injectors. One is a high pressure direct injection, and another one is low pressure port injection. Port injection means where the injection takes place inside the intake port, where air is coming in. And direct injection is where fuel is being directly injected into the cylinder. This is the schematic of the engine. This is a single cylinder engine, which has a direct fuel injector and a port injector. It is operated, powered by a dynamometer, and then air is being sent through a surge tank, passes through the intake plenum, and goes into the engine cylinder. What we are doing here is essentially comparing the water and water methanol blends on combustion performance. The way I carried out the study was to look at different blends of water methanol prepared with varying volume concentrations. That is 75% water, 25% methanol, 50% water, 50% methanol. Now you might wonder why are you doing this different concentrations? What we're trying to understand is water actually acts like cooling the engine temperatures, whereas methanol, it has a higher latent heat of vaporization than gasoline. At the same time, it acts as a coolant. At the same time, it can also act as a fuel because methanol can participate in combustion. So what we are trying to see here is if we are able to see some improved benefits by adding methanol to the water, and that is the point of interest where we are trying to look at different concentrations and trying to understand the impact on the combustion performance. Some terminology with what we are trying understanding here. First one is water fuel ratio. This is a normalizing parameter. How much the mass flow rate of water to the mass flow rate of fuel, how much amount of fuel is being sent, and how much amount of water is being sent. So we try to adjust the water fuel ratio. And the other one is mixture fuel ratio. So the mixture is a blend of water and methanol. If it is only water, we call it water fuel ratio. If it consists of water and methanol, we can call it as mixture fuel ratio. And then fuel efficiency, it is what is the power produced to the fuel chemical energy. And then this is another parameter which is normally used to characterize or measure the combustion performance. It is called combustion phasing, CF50, which is actually the location of 50% mass fraction burned. This is how the fuel burning takes place. This is how it progresses over a certain duration of crank angle. And CA50 is the location of 50% mass fraction burnt. And normally CA50 of 8 to 9 degrees, just after the top dead center, is kind of optimum timing. So here what it consists of, what is shown in these two figures, is the performance or the characterization of the combustion performance by pressure and heat release. Normally when combustion takes place, there is pressure increase associated with it, and that is what is seen here. You are seeing that when combustion takes place inside an engine cylinder, it is associated with a temperature and pressure increase. And because of temperature increase, there is some heat release to the outside, and that heat release is shown here. So what you are seeing here is seeing different fuel blends. First one is blue, is where there is no water injection. So only fuel is injected, no water is there. You are not injecting water, only fuel and air mixes, combust, and then pressure increases. And then 100% water. So there is fuel and there is 100% water. So the mixture only consists of water. There is no methanol in it. The other one is water methanol 50-50, which is 50% of methanol by volume and 50% of water by volume are mixed to form a blend, and that is added along with the fuel. Next one is water methanol 75-25. So this is 75% water, 25% methanol. The last one is 100% methanol. So in this case, in the green one, there is fuel which is gasoline or petrol, and the other fuel is methanol. It is used as a coolant as well as a secondary fuel. So if we have adjust the spark timing such that they're all they have the same 50% mass fraction burnt location, how do the pressure profiles look like? This kind of tells us how the combustion signature would be for a particular case. And at this condition, what we notice here is that these are almost overlapping on one another. There is a very small variation. And however, even in this case, you can very clearly see that there is 100% water is slightly better. Whereas here, without the water injection, you might wonder why is this so low. As I had initially told, these spark ignited engines are limited by engine knock. So we cannot advance the spark timing before engine knocks. So this is the limiting spark timing. And to adjust the spark timing, we will go and inject some water, which cools the temperature and allows adjusting the spark timing. So in all these cases, the spark timing is not same. This has a very retarded spark timing. The spark timing is much later, whereas in these cases, the spark timing is much earlier. So adding water or adding water methanol is enabling us to alter the spark timings to reach a point where we can improve the efficiency. Next, what happens is, this is the impact of water injection on the CA50. That is the 50% mass fraction burned. What you're seeing here is the variation of CA50 or 50% mass fraction burned with respect to pure water, 75%, 25% water methanol blend, 50-50 water methanol blend, and pure methanol blend. What you can see here is our target is we need to reach this condition, CA50 of 8 to 9 degrees after top dead center. So when you are injecting only pure methanol, you just have to inject 0.3 mixture fuel ratio to reach this advanced spark timing, advanced combustion phasing. Whereas if you start injecting water, you will have to inject almost the same amount of water as the amount of fuel. So a mixture fuel ratio of 1.03 means the amount of water that I am injecting into the engine cylinder is almost the same as the amount of fuel that is being injected. And that will lead to a same CA50 of close to 8 to 9 degrees after the top dead center. Now, essentially what is happening is the in the blend of water methanol, if you increase the percentage of methanol in the blend, then what happens is, because methanol also acts as a fuel, it will be able to advance the combustion phasing much earlier. So even a lower quantity of methanol would be able to reach that combustion phasing at a slightly lower mixture fuel ratio. So the outcome of this is like, to reach this point, to reach a CA50 of 8 to 9, if you are injecting water, you will have to inject a lot of water. If you are injecting methanol only, you can inject only a small amount of methanol. If you are injecting different blends, you will have to inject these. So improvement in the combustion phasing will take place due to this. However, there is one downside to adding methanol to the fuel. What is that? Is it is because of the property of called calorific value or lower heating value. So what is the amount of energy that is generated or provided by burning 1 kilogram or a certain unit of methanol is shown here. Normally gasoline or petrol has a lower heating value close to 44 megajoules per kilogram, whereas methanol is much lower than that. And as a result of which, what happens is, for generating the same energy output, you will have to supply more amount of methanol, which is what is seen here. This is a specific fuel consumption plot. What it essentially means is, what is the amount of fuel that you are consuming to produce a certain amount of power. And if you see here, the specific fuel consumption for the methanol is, for a complete methanol case, is significantly high than with water injection. So here what you're doing is, you're injecting water and you're supplying only fuel, whereas here you're supplying methanol in addition to the fuel. There is no water. So in this case, you need to supply more amount of methanol to reach this particular condition. So the total fuel consumption is still high because methanol has a lower heating value than gasoline, which will mean that it needs to be supplied in larger quantities. It has a lower energy density. Now the impact on the emissions. We saw the emissions of with respect to water fuel ratio. Now you can visualize, when water is injected, what happens is it kind of dilutes the mixture, and once dilution takes place, the emissions tend to increase. The hydrocarbon emissions, the combustion will be slightly delayed. But for the NOx emissions, which are a function of temperature, so higher the temperature, higher will be the NOx emissions. So when you inject water, the NOx emissions tend to reduce gradually because of reduction in temperature, whereas when you increase water concentration, you are essentially increasing hydrocarbon emissions as well. So these are counteracting effects. HC emissions increase because of water injection, increase in water injection quantity, whereas NOx emissions decrease because of that. So as engineers, we'll have to do a trade-off and say, okay, this might will have a limit on what would be the benefit of adding water on the NOx emissions. So we'll have to do a trade-off on that. Now, comparing the different strategies, we did test the regular fuel without water injection and looked at the efficiency, overall efficiency, and we found an overall efficiency of 37.1%. This is a compression ratio of 11 is to 1 engine. And then if we use a premium fuel, which is 93, AKI 93 fuel without water injection, we get a 39.2%. Whereas if we use regular fuel with water injection, if we implement water injection or water methanol blends, we get an improvement close to 39.7. If I increase the compression ratio, because I'll be able to use more water. Then if I'm able to improve, increase the compression ratio, then I'll be able to improve the efficiency by close to 10%. So this is a benefit of including water injection, is that it allows increased compression ratios, and we will be able to see some improvement in the indicated efficiency, and also subsequently some reduction in the NOx emissions as well. However, there is some downside to it in that it increases the HC emissions. So we did extensive studies on the water injection. Long story short, what does this do? This is an advanced combustion strategy, and it allows the engine to be operated at higher compression ratios, enabling increased efficiency. So it's essentially, if you increase the compression ratio, your ideal cycle efficiency will be increased, and water injection allows that. And we have also seen improvement in the combustion stability with the addition of water or water methanol blends. And we've also seen reduced exhaust gas temperatures and reduction in NOx emissions. There were some higher burn durations, but we could advance the spark timing, or we have control over the spark timing. But there are some practical challenges on increasing mass of water significantly, because it will not be able to completely vaporize. And that comes to the second part, which I'm doing on the sustainable aviation fuels. So essentially, this is a project which I'm doing now as a postdoc at UW Madison. What we are trying to do here is we are trying to use multiple fuels for aviation applications, for aircraft applications, in the sense that, can we enable technologies, or can we build technologies which allow engines to operate on multiple fuels? If we are able to do that, then what happens is, we do not depend on only one particular fuel. Normally jet fuels are being used for these aircraft applications, right? So if we are able to use some sustainable aviation fuels, which are blends of ethanol or jet fuel and all, then if we are able to enable technologies that allow these aircraft engines using any type of fuel, then it reduces the fuel dependency. And also, by using sustainable aviation fuels, we will be able to reduce the emissions contribution to the environment as well. So this is the motivation for this particular project that I'm currently working on. The challenges of operating these aircraft engines are operating at extreme temperatures and high altitude conditions, where the air is low, the mass of oxygen available is low, and there is a huge wide range of operating conditions, and there is a large fuel property variation. So we are right now investigating multiple fuel blends, and using ignition technology to aid combustion at those extreme temperatures and high altitude conditions. So this is the aspirational goal, to use a multi-fuel capable hybrid electric engines. Currently, these are all some of the applications. And we have found some promise by using alcohol to jet blends for multi-fuel aircraft in multi-fuel operation. The outcome of that would be, if you ask the question, so what? We can use these technologies for ground vehicle light duty operation as well, which is where my vision forward, or conclusions would be like, globally, we have enough pathways for co-optimized fuels and advanced combustion engines. Alternative fuels along with advanced combustion engine strategies offer viable solutions for power generation. The viable solutions is very, very important. We need to understand. And from an Indian perspective, there are some challenges, but there are some resources which we can tap into. And multi-fuel capability with clean and low reactivity fuels can lessen dependence on fossil fuels significantly. For an Indian perspective, since we depend so much on imports for fuel, for fossil fuels, multi-fuel capability using these alternate fuels can significantly reduce the dependence. And going forward, we'll have to focus on local, low carbon and sustainable fuel sources for power generation. It is more specific to India, but also globally as well. So the key takeaway after all this talk for close to 1 hour, even if you have not understood anything, low carbon fuels are needed to combat climate change. And you might have heard many things about different transportation modes of powertrains. what I would like to say is different modes of powertrains can coexist in the future. It will be a combination or a mix of solutions that include internal combustion engines, electric vehicles, plug-in hybrids. Everything will be able to coexist in the future. It depends on where and what, and dependence on the resources and on the local challenges. So my key takeaway would be that we do not, at least for the next few decades, will not have to worry too much about only worrying about one particular form of transportation. Different modes of powertrains can still coexist in the future. With that, I leave the session for questions. Thank you for your time, and I'm ready to answer any questions if you have.
Uh, Thank you, Dr. Niranjan. With this, I would like to take up some questions which are posted in our question answer box and chat box.
Okay.
Yeah, so in the road transport, the data from our world that what you are showing, you uh, do you have the data of percentage of personalized vehicles versus cargo versus public transport worldwide?
Uh, yeah, at this point, I do not have the exact, and it depends. Like I showed it for global, right? And it depends essentially on each country as well. Right now, transportation, if you look at it, globally, it is like 17%. Whereas if you look at US, it is close to 27%. Whereas if you look at India, it is close to 17%. So it depends on the country as well, and it is slightly the range. What I would say is the range is slightly the same. It's between 20 less than 30%. Having said that, it depends essentially on the country. Here you have some higher percentage of heavy duty trucks as well, whereas it depends on in Europe it's slightly different, right?
Sure. So I will take a few questions.
Hmm.
So this is by Dr. AVS Shiva Prasad. He says, I might have missed that part I'm going to ask about. Has any particle velocimetry imaging been done? Or if it is not done, isn't velocity distribution an important factor in the study of spray atomization?
Yes, that's a good question. Particle image velocimetry is, at least in my scope of research, I did not include that. But I have also done some studies where I have investigated the velocities near the flow field close to the spark plug. So the goal being, how do we enhance flow field near the spark plug? And right now, normally the velocity close to the spark plug is of the flow field close to the spark plug is 20 to 20 meters per second. So there are some techniques which could be used to do that, but in my scope of study, we didn't involve that.
Okay, thank you, Dr. Niranjan. So this next question is by Professor Revankar. Now, what is the possibility of injected water contributing energy by splitting into hydrogen and oxygen? This is in the light of an alternative technology claim of water engines that are fueled by water.
Yeah. What this technology talks about is, again, it comes down to the last point. One is um, offering a viable solution. So essentially, using this technology, what what are the changes that you can do to an existing engine? If you have to include water injection, we can do a small change in the sense that you can install a water tank and have an water injection system, and that would offer a feasible solution in the sense that it would not cost too much. However, we will have an improvement in the efficiency. But I take that point in the sense where he says water can be converted to hydrogen and oxygen. That is another entirely new technology, right? We are talking about, we are essentially comparing two different technologies, but that's still possible. What here I'm talking focusing on is a viable solution that can be implemented with not significant changes to the existing design.
Sure, thank you. There is a follow-up question by Dr. Revankar. Can cogen be a more feasible option to enhance efficiency in transport sector?
Can you
Uh,
repeat that?
can co-generate, I think cogen is cogeneration, by a more feasible option to enhance efficiency in transport sector? What is the gain in BTE of engines operated on advanced combustion routes?
Yeah, there is this option of cogeneration as well. There is one research group at Michigan Tech which is looking at this aspect, and they are actively looking at this on high BMAP engines. That's still a part of research, that is active research that is currently going on. And the second question was, what is the improvement in the brake thermal efficiency? For that, this includes different multiple operating conditions, right? You're talking about different torque regimes and all. So at this point, I'm not sure about what would be the best way to answer that. But the water controller or water injection controller that we build currently is being worked on. What it does is it takes into account all these different torque map regimes and tries to build a controller which can identify how much amount of water needs to be provided, and how much is the amount of improvement in the performance that is generated inside the engine.
Sure, thank you, Dr. Niranjan. This is by Professor Banapurmat. Is this a direct gasoline injection or PFI engine?
Yeah, we did too. I injected water through a intake port or a port water injector, and injected fuel directly into the engine cylinder. And I also swapped this. I injected water directly into the engine cylinder and did the port fuel injection as well. The intent was, initially there was port fuel injection which was done earlier, and then we switched to direct injection of fuel, because we saw that there was better control of fuel and it improves the fuel economy and all. But the downside to that is the particulate matter emissions with the direct injection. And this comparison that we did was, um, kind of, it provided new insight in the sense that we saw some improvement in the efficiency through injecting water directly into the engine cylinder and port fuel injection. So fuel was injected through the intake port and water was injected directly into the engine cylinder. Now, what this does is it is improving the efficiency because of direct water injection. And port fuel injection, what it does is it allows more homogeneous mixture to form. And the benefit of that is it reduces the PM emissions as well. So we are kind of seeing best of both worlds, in the sense that you are getting the benefit of improved efficiency due to direct water injection and reduced PM emissions due to port fuel injection as well. But I would still hold my horses and say that this was observed at only a certain operating condition, which was not so high load. So it would be interesting to see that at multiple loads as well.
Okay, you can unshare your PPT if you want.
Oh, yeah, yeah.
Uh,
Okay.
yeah, so I myself have a couple of questions before I take the
Mhm.
other question. Uh, is the water injected should be checked for the dissolved solids? The hard water may damage the engine cylinder assembly.
Yeah, yeah. I think I have a photo. Let me see. Um, I actually had a photo of how, if I inject impure water, we normally use distilled water, devoid of any minerals and all. And if we use water frequently, normally the experiments that I ran, what I used to do was, at the end of the day, once I run the experiments, I check the lubricating oil. If I inject more water, then I would see that the lubricating oil loses its viscosity properties, right? And then that would be a problem. So every time I run these experiments, I'll ensure that I'm not injecting more than what is needed. So I have kept a water fuel ratio of close to 1 or 1.1. And if you see, this is by controlling the type of water that we are injecting, distilled water. And but we have seen that repeated usage of water injection for longer durations of time, it starts to affect the lubricating properties of the oil. And I'm trying to see where the photo is, but it's almost, it looks like an espresso. Espresso coffee,
Okay.
the lubricating oil looks almost like an espresso. And eventually, if you store that, or if you just keep that aside, you will see the water settling down and oil just staying on top. You'll see a very clear distinction between the two. But we have ensured that those aspects are taken care of by using distilled water.
Oh, sure. Thank you. And then, can the injection happen in small amounts while suction stroke is happening via manifold injection or intake valves itself?
We
So,
did that. Yeah,
intake valves.
we did that. Right now, the port water injection that we're talking about is done during the intake stroke. Just when the piston is coming down from the top dead center to the bottom dead center, and the intake valve is opening. So we've also tried to investigate whether injecting water when the intake valve is closed, or whether injecting water when the intake valve is fully open, or in between. We try to do a sweep there and try to see if there is any variation in the vaporization, because now there are multiple heat transfer processes that take place there as well, right? If we close it, if we inject water while the intake valve is closed, then we'll have water collecting on the walls of the intake valve. So
True.
that leads to different heat transfer
Issue.
phenomena. So uh, we've done that, and we have noticed we injected it slightly during the intake valve opening phase, and we found that that was optimum actually.
Yeah, because the pressures would be on lower side, so your saturation
Yeah.
temperature would be lower. So, the question from Professor Banapurmat is what are the typical methanol injection pressures adopted? If the blends are used, will there be a separation issues during injection? Have
No, we that's a good question. We have not noticed any separation issues at the pressures that we injected. Although we injected through the intake port, we did not notice much issues with the separation. We've also even tried doing an emulsion, just making a blend, making an emulsion, water methanol emulsion even. But we didn't see any significant issues with that.
you use surfactants also in this? Like,
No, it's
no,
just a volume splash blending of methanol and water, and then sending it through a low pressure injection system. And because it's going through the intake port, we just send it as a splash blended uh, fuel.
okay, so a few questions will take up. We have another 4 5 minutes. What are the key technological challenges we can expect for its sustainable development?
Key technological challenges for sustainable development. Again, it depends on where you're trying to implement. Whatever might work in the US might not work in India, and even whatever might work within the US. Let's say, for example, in whatever works in California might not work in Michigan or even Madison, because we are talking about different resources that are available. So uh, I think we need to look at what are all the available resources and where the resources can be tapped, and try to find solutions to which are very specific to those areas.
True.
Because even in India, if right now, I think the most important discussion that's happening is like climate change. We need to transition to vehicle electrification, but we need to add a caveat in the sense that in India, even today, how are we generating electricity? We are still depending on coal and natural gas and fossil fuels, which are again dependent on imports and which are again harmful. So we might ensure that the emissions coming from the tailpipe might be negligible, or there is no emissions, but we are still contributing to the emissions through the generation of electricity. And until and unless we are able to get into some renewable means of generating electricity, we'll not be able to achieve zero emissions or anything. So for
Yes.
some countries where they can generate renewable energy, like Europe, like Denmark and all, Netherlands, they can use renewable sources to generate electricity.
Correct.
They can implement electric vehicles or anything, they can transition to it, but we can't use the same solution and apply it everywhere. We need
Mm-hmm.
to tap into the local resources and then see, okay, which one is sustainable, and is that feasible as well. Again, we can do it, but at the same time it has to be feasible and it has to be affordable. We
Correct.
cannot take that, we cannot ignore that, right? I
Yes.
can still make an engine which costs like probably 1 crore,
Yes.
but who is going to buy that, right?
Yes. So the center here is actually working on this Sustainable Development Goal 7, which is affordable and clean energy.
Affordable
That's
energy, right? Exactly.
affordable energy.
Affordable energy is like, how do you make these technologies that affordable? I can still have an electric car, but if it is going to cost me like 3 times the existing car or 2 times, is the customer going to buy that essentially?
So a couple of questions regarding the other forms of blending. So whether liquid CNG or LPG can be blended with petrol, since both are petroleum products for current technology.
Yeah, there are dual fuel operations we have also carried out, and there are enough dual fuel studies that have been carried out with LPG, with CNG as well. Natural gas, same whatever we have done here with respect to injecting water through a port injection, natural gas is injected through that. That's there are multitudes of studies that have been carried out with that.
So and following up with that is if we use this ethanol methanol blended fuel or any alternative liquid fuel, what kind of modification should be done and what will the effect on the engine life? So this is I think regarding the engine modifications
Engine
required.
modifications, at least with methanol, one of the drawbacks of methanol is it corrodes the fuel system very quickly because of its oxygenated molecules presence, right? So it has an effect of corrosion on the fuel injection system, so to say. But one way that could be achieved is like blending some limited amounts of methanol and also having a control which doesn't ensure that methanol is being used for a longer time. It's only for a certain range or for certain operating conditions where you can use methanol and get gasoline, or methanol and ethanol, any of these blends, and still have a long enough engine life. But that's the goal, right? If multi-fuel operation is that, can we reach a condition like if you go to a gas station or a petrol bunk, if you go there, you now are limited by what your car or two-wheeler is. Like if it is a petrol car, you go and inject petrol, right? Can we reach a stage, or can we enable technologies that you go there, you can inject diesel, gasoline, methanol, ethanol, or any other blend and still be able to run that? If we are able to develop those technologies, and that's probably the vision right now, we are doing that for aviation fuels, aviation applications, but we want to extend this, or my thought is like extend this for ground vehicle applications as well.
Okay, that also probably answers Mustafi's question regarding ethanol blending with gasoline.
Yeah.
Hello, sir.
Yes,
Hello.
Professor Evankar. Yeah,
Hello.
hi, Professor Evankar.
Sir, I wish to have one flash question if you allow.
Okay, go ahead.
Hello.
Yes, yes, go ahead.
Hello.
Yeah, you are audible. Go ahead.
Uh, yeah, sir. Dr. Niranjan. Hello.
Yes, I can hear you.
Given a choice between generating more energy and conserving energy, what would be a better option for sustainable development?
Given an option, generating energy through sustainable means is what I would say.
Yeah, normally they say that 1 megawatt is more costlier than a megawatt.
Yeah,
Hello.
I mean
Yeah.
it again depends on how you are generating that, right?
Yeah.
You still can, essentially you can still regenerate some of the exhaust that is coming out of the engine. You can still use that as some useful energy, you can get some useful energy out of it, that's still possible. But again, it again boils down to what are all the feasible alternatives and what's the cost to benefit analysis, because technologically you can do many things, but at a policy level you'll have to think about a larger aspect, like how it is feasible, how viable the technology is. If it is going to cost me like several thousands or several lakhs of rupees for implementing or for getting a small energy benefit, would I still do that? So it's again a energy policy driven decision.
Thank you, sir.
Thank you,
Thank you.
Professor Ivankar. So thank you, Dr. Niranjan. I will, so we would like to, I'll end the question answer session here. I will also send you the questions that's been posted by
Yeah.
email to you. So we'd like to heartily thank our guest speaker, Dr. Niranjan, for the Trees Talk 15 for the invaluable time. We also thank the audience for their questions and interactive discussions. Next talk under Trees series is by Dr. Pradeep Malaji, Associate Professor and Vice Principal, Academics and Research at Dr. P.G. Halkatti College of Engineering at Vijapur, Karnataka on 21st of October 2022. So thank you again,
I
Dr.
can show you
Niranjan,
the
for
picture
your
of
time.
the I
And
can show you the picture of the blend if you
sure,
uh,
please.
just a moment.
So do you have these water injections in CI engines as well?
Yeah,
Okay.
they are there as well.
Mhm.
Just a moment. Um, uh,
Yeah, share the screen.
yeah, I'm just searching for. Yes. Let me share my screen. This is how it looks like. So this is the water that is deposited. This is the oil.
Okay.
It's completely discolored.
Mhm.
And this is after keeping the lubricating oil for probably a week
Uh-huh.
after it was used, and now it's like it has separated clearly.
Sure. Yeah.
Yep.
So this is
Yeah.
SAE oil something.
Yeah. This is SAE 15W40.
Okay.
We use that because we are operating at slightly higher temperature, so we wanted to have a slightly high viscous uh, an oil which wasn't having a variation in viscosity even operated at high
High
temperatures.
temperatures. Okay. Okay.
Yeah, because the engine is like compression ratio of 11:1, and then we increased the compression ratio to 15:1. So we didn't
Mhm.
want we wanted the oil to be able to withstand all those high temperatures and all.
Thank you, Dr.
Okay,
Niranjan, for this
thank you.
wonderful talk and interactive, informative sessions. A lot of participants have appreciated your work. Thank you again.
Thank you. Thanks a
This,
lot. Thanks for having me, and thanks for these questions as well. Thank you, Dr. Dheeraj, for inviting me to present my work.
my pleasure. Thank you,
Thank you
and
so
see
much.
see you soon here.
Sure,
Next
sure.
weekend.
See you
Yes,
soon.
please,
Yep,
please,
yep.
please visit. Whenever we are
Sure.
visiting IIT, this part in Karnataka, you are from Karnataka, so please visit IIT. Yes,
Yes, I'll
we
take
have to
this.
go.
I thank you for the invitation. I will plan once I have some solid travel plans. I'll contact you, and then we'll see how it goes forward.
Definitely.
Thank you so much.
Okay. See you. Thank you
Thank
again.
you, everyone. See you. Bye. Bye.
Bye. Thank you, everyone.